Hello, everybody. Welcome back to Module 4 of our Informatics 109 course. Kind of covering everything. It was an intro week, but then we looked at hardware. And last week we talked about the data that we put on our and how it actually stores those raw facts for us so that we can do things with them. Next logical step is going to be taking that a step further and getting into software this week. I guess the degree program this module aligns with would be software development. So looking at programming, where we grab that data and we do stuff with it instead of looking at being humans and like printing out that list of raw facts and trying to figure out what to do with it in our minds. We got to automate some of those processes. This is the subject I normally teach the high level versions of. So I will try not to go down any rabbit holes. Y'all probably know I'm always distracted and we'll start doing them. So software development is what I usually teach the high level courses on. And so I'll try not to go on get complicated, try to keep it somewhat simple. There's those ones. The last of those 4 foundational skills is this week. We saw the productivity software, the Office documents, spreadsheets, slide decks, doing that lab about Access, which is the whole Office suite, even though some of our Office suites, Google Office Suite and Max Office software, they don't have the local database option, but there are plenty of databases out there to use. So we saw all those, and the last one was the productivity software, which I guess I could have opened up even ahead of time. We jump over here and look at this. It's probably the easiest one as far as using, but there's lots of ways to work with it, and in general, a little bit of organization goes a long way. And that's what it is, this making sure you know how to organize all the stuff on your computer, structure it. So just confirming you know how to do stuff with the setting up files and folders and keeping all that straight. You don't save everything you do to the desktop, or if that's the way you like to work, you know how to organize it nicely instead of just saving it all to the desktop. And y'all have probably seen it. Some people will have the best 3 monitors wide, and it's all the individual files are spread out there. And really like to work that way. We want to make sure that you can do the other ones. So file management stuff, pretty straightforward. You're just going to create a couple folders, put some files in them. But I have a feeling most people know how to do that already. Right? You've done that before. So what I tried to ask for here is try to learn at least one new way to do it. Lots and lots of ways to do it. I'm going to go ahead and assume everybody knows how to do it with the mouse immediately. The 2 most productive ways heading into IT, the best ways to learn, make sure you know how to do, would either be hotkeys or the terminal. So with hotkeys, if you're on a Windows machine, you can push Windows E and open up File Explorer. And that has an Apple phone, so you can hit tab to go around, but you can also push Alt D, is in the second letter of the word address, because A was already used. Alt D goes to an address bar on Windows machines. Then we can just enter some other folder, documents. I'll go with my working directory. Control Shift N will make a new folder here and do all the hotkeys, give that a name. Name. Then we hit enter, we can go into it, navigate around with just those keys. So we have way more control with the keyboard than the mouse. That'd be a really good one where you're heading into IT. The other one, which is also going to be useful for IT people, is going to be the terminal. Some sort of terminal, PowerShell, command prompt, which actually command prompt doesn't do anything anymore. Windows removed it, and they got a lot of backlash. So they put a fake one back in that all command prompt does is forward the instructions to PowerShell. But PowerShell runs the old command prompt instructions. So you could just open PowerShell and type the old command prompt instructions there. So that fake one actually restricts capabilities because it takes all the PowerShell stuff out of there. PowerShell knows Linux commands too. but they updated it and got it. People don't like change. They updated it to a modern scripting language. This is software. That's what it was. I'll talk about that. But some sort of terminal, a bash shell if you're on Linux or a Mac, or a Z shell. Is anybody on a Mac? So I'm going to use the keyword shortcut, push Windows X. That gets to all of your computer management software. So the things for controlling your computer are shortcutted there. And you should see terminal or PowerShell or command prompt or something there. If you're on a Mac, the quickest way is to go to Spotlight. It's like the easiest key. Push your command space, pulls up that search bar to search for things in your Mac. Just it's the easiest hotkey. Just press your thumb down and search for terminal. And it is called terminal on a Mac. PowerShell, those are ones I just mentioned: bash, command prompt, Z, which is sort of a cousin of bash. You have to get pretty advanced before you can find a difference between Z and bash. They're the same type of pathways, just like slight differences, and it gets really advanced to find any significant differences between them. But those were made back in the 1970s. They were improved along the way, but well, back then RAM was a very precious commodity. RAM, the 1970s, 1980s, to the early 90s even, RAM was a very precious commodity, and we definitely didn't want to waste it on the computer experts. So everything was abbreviated. So there's that. We used different syntaxes back then. Different terminologies changed along the way. Like if anybody's ever used the Vim text editor, copy and paste, the shortcut for copy is Y, because one of the alternate terminologies we had instead of copy and paste was yank and put. So it went with Y for yank, which I think that would have been a better thing to go on. I like that wording a little bit better, but there's other things. So what we call things changed since those were created. Syntax has changed drastically. So by the early 2000s, it was time to update those little terminals. Technically, it's terminal emulator. So way back in the day, we have the mainframe, that's the CPU and the memory and all that stuff. And then we'd plug in something with a screen, and that was the terminal. So how we would control the mainframe was a completely separate device. And it's sort of a good system. So now our computers have terminal emulators, just a little someplace to input text, basically, to give all the control. It's full control of your machine. Actually, more control than you would have with the mouse. There are certain things that anytime you click a button on a mouse, like if I come over here and click, let me close on Chrome. If I come over here and click the Chrome button, it starts start the browser. What that does is it runs this instruction in the background. Run start Chrome, or start Chrome with ivlearn.ivtech.edu. So we just run it. The picture that we click on with our mouse just runs that instruction in the background. And not all of the instructions we can pass to the computer made it to the pictures, because there's some things we want to resolve for the computer experts. Really, we don't want the average person having access to them unless they really know about computers. So moving it into keeping it away from the icons, make sure that somebody has to at least be on a pathway to being a computer expert before they even know how to run that functionality. Help prevent little accidents and breaks and things like that. But this is the direct instruction of our machine. By the early 2000s, it came time to update them, because all of them in existence had been around. We're kind of outdated as far as language. Everything was abbreviated in order to save RAM, but we didn't have to save RAM anymore. Syntax had changed was the bigger one. So the operating system started working on new modern scripting languages for the operating system control language. That's how I refer to it. It's the programming language to directly control the operating system. And Microsoft finished theirs first and did an amazing job. Everyone thought Microsoft They do so many annoying things, but every once in a while Microsoft does when they do the good things, they do them so good that it just blows everything else away. It's like, oh yeah, that's why they're so big. PowerShell was one of those. And actually, Linux and Apple abandoned their plans to make a modern scripting language and just went with compatibility with PowerShell. Microsoft did such a good job. The other systems are just automatically compatible with it. Because they weren't going to do better than what Microsoft put together. So modern syntax and stuff, but as far as file structure, files and folders, the directory structure, that's probably a good starting point. So the old commands work, so we can still use the abbreviated ones like CD, which there were slight differences. This is a good example of the difference because on a bash shell, CD is a function. It means change directory. We'll talk about that at some point today with OSHA. And on a Windows machine, the old command prompt, CD was a variable. It meant current directory. So same abbreviation, but it did two different things. In general, it tells us where we're currently at. Change to a different location. Change directory makes more sense. So we can change to a different location. So change directory, go into the documents, and the delete folder where I normally work with things. And the old abbreviation was the same on every system, make dir. So make a directory. We want to make a new folder, make dir, I'll call it my folder. On a Windows system, it was dir to list things out, or on a bash, it was ls for list. PowerShell knows both of them. So PowerShell knows the old languages and the new language. So that would be my recommendation for one to use, because you get a nice sampling of things. You can mix and match the different ones together and stuff. Then again, we can change directory into that new folder, which I already forgot what I called it. My folder. So change directory into my folder. And I guess for the assignment, you have to nest things a couple folders deep. Then put some files in them. We can make new files. There's a couple ways to make new files. The easiest way is to have the software make the file for you. So I use like the Sublime text editor. So I could put SUBL for the Sublime text editor and my file.txt. And have the text editor open that up, create a new file, do all the editing, and save it and close it. Oh, and I just hit Control S. I think y'all are probably familiar with that for save. Control W closes the window. That's another very useful hotkey. So we'll set out and we'll see the files in there. So for most everyone, my recommendation would be to use the terminal for that assignment. Try to learn something new. So lots of different ways. Depending on your level of computers, right? There's always further you can take it. And if you go in the hit Windows X to go into the control things, and where's a good one? Your management, I have it. I guess so. Under computer management is task scheduler, or like cron on the Linux system, or you can just search for task scheduler in the start menu and get right to it. But you could just set something up that creates a folder 5 minutes from now, and 1 minute after that, it creates 2 more folders inside of it, and 10 minutes after that, puts 3 files in all those different folders and stuff. So you can always take it further. There's always something new to learn. So that was kind of my request. I assume people already know how to create folders and put files in them. But I am going to ask that you try to learn a new one, and when you submit it, just let me know what you did to create the files and folders. If you use the terminal, screenshots are nice. You can just take screenshots. Everybody know the shortcut for that? Windows Shift S. If you're or a different system. So Windows Shift S, if you're on Windows, pulls up this little thing for the first one. you get these crosshairs and you just take a picture of the screen, which Zoom has some of the resources occupied. If Zoom wasn't claiming the screen right now, a little notification would pop up showing that. I have mine pre-configured so that they save because I'm on Zoom calls so often. So it's already saved over in the pictures folder, but usually the notification pops over. It's on the clipboard, so you can immediately go hit paste somewhere and it'll paste it in there. Or in the notification, there's some editing things. You can like grab a red pen and or a red pen simulator and draw mark up the picture and things like that. So Windows Shift S. If anybody's on a Mac, it's Command Shift 3. We'll get the whole screen one. That's like this one over here, and you just click the thing you want to take a picture of, the particular window you want to take a picture of. And on Mac, Command Shift 4 will give you the crosshairs where you cut out, just choose a small section. If everybody uses Chromebook, it's Shift everything button desktop. So in the middle of if you don't know that by name, in the middle of the top row on your Chromebook is a button that has a picture that looks something like this. That's how you switch between multiple desktops. If you push Shift and then the everything button, which has the search bar. So Shift and then this button and then the one in the middle of the top row. That gets the same, that pulls up a little piece of software like Windows has where you choose what type of picture you want, and you either have crosshairs for a section of the screen or the whole screen. That's definitely something that you want to include. Actually, I'll say that now. Yeah, I'm gonna edit those instructions maybe when we're on a break and include submit a screenshot because that shows up a lot in IT, especially as things have moved online. You'll go to some online simulator, do your homework, and then there's not really a good way to get that back to the teacher. So screenshots are pretty common. So I'm going to add that to this week's instruction that after you make the files and folders, go ahead and take a screenshot of it. Just make sure, I guess like the rest of the confirmation things to confirm that you know how to take screenshots on your machine. Add screenshot to 4. It should be a fairly simple assignment. Just tell me which thing you chose to do that. There's lots and lots and lots of ways to do that. The terminal or the hotkeys would be my recommendation. That would also help in, if you go to Google and look for a list of hotkeys. I just showed a couple, but Google a list of hotkeys because you're probably going to want to have a good reference bookmarked or something so you can quickly get back to those because there's a lot of keyboard shortcuts. It takes a long time to learn, but if you learn one a week on your way through school, there's a lot of weeks in a 2-year degree program, right? What is that? 8 times 2 is 16. There's excluding summers. I guess everybody here is going to go through summers, so we got that. So 2 16 weeks, 32, and another 8 weeks. So 40 weeks a year of school in 2 years. So 80 weeks. You learn one a week. You'll know 80 shortcuts, and one a week is a very, very small number. So just stretch it out over time. That way you're not overwhelmed all at once. That makes a big difference. Is there something else I can oh, just a note. Please pay attention to the due dates on discussion boards. Because remember, the discussion board, the final discussion is due like tonight, but there's that post and reply section. So your initial post was actually due last Friday. I think there was a couple turned in this week after that initial post, and do mark a point or two, a couple points off for being late on that. I apply the same policy, but around the whole numbers. So it's like 3% per day, but it comes out to basically comes out to about a point for every 20 hours. Past Friday at 11:59 p.m. it is. So same policy, but please make sure you get the discussion board posted on time for everybody to reply to. I thought this week's discussion board was kind of interesting too. From what I looked at, it looks like there's some neat comments in there. So, the most important of it, right, the history of computing is kind of large. It's quite a bit. So I asked for what do you think is the most important from each decade? Like the 1950s or in the past, we can go back over the centuries. Every decade of the century, but they go back to major inventions that were just on the way to computing. Like all the way back to electricity or even in ancient history, the abacus, things like that, other machines that humans have had over history and show that progression. What do you think is the most important? So I always find it interesting. It's a good one for discussion too, but what people tend to say the same over and over and over. You'll see the same thing showing up for certain decades over. It's kind of weird when somebody doesn't point out transistors. But every once in a while, somebody else will say something different. And then there's some debate on how to show that. We're talking when two people knew how to make them in a laboratory and they made 5 or 6, which would put it in the 50s. Or are we talking about when it was actually produced and computers started being based off of that, which would have been the 1960s? It was right there at the border. And technically in the 50s, it existed, but 3 people at Bell Laboratories knew it existed. And they had one or two prototypes working. It didn't really spread until later. So there's some little wiggle room like that too. When was it invented versus when did it take off? I thought it was an interesting discussion. But the reason I'm on the notes was please pay attention to the 2 due dates. The original one I think is due on Friday or Saturday. It's written in the instructions on the discussion board. Post by some date and then reply by the final submission date. That was the side notes that I had. Anybody have any questions before we jump into our next topic here today? Okay, so next up, we'll look at hardware. Then we looked at how that hardware stores data. So we need to do stuff with it. That's where we get into software. And in the modern world, I don't have it. Y'all have already heard that word. You know what software means, right? There's the technical definition right from the dictionary, which I thought was not even a very good definition. I was actually going to write it down because I thought it was kind of a lousy definition. It's not very helpful. Programs and other operating information used by a computer. So that's what's actually written in the dictionary. I didn't think that's a very helpful definition. I guess it fits with the dictionary, right? That book will tell you everything there is to know about a language as long as you already speak that language. As long as you know everything that's written in the dictionary, it's a really useful book. That's kind of what this definition seems like to me. As long as you already know what software is, that's helpful. So colloquial, sort of a colloquial definition, something that would be a little more useful. Let's go with set of instructions. Data or programs to operate computers and execute specific tasks. That's a little bit more detailed because it's still kind of like the other one. Still, I kind of have to know what these words mean in order to make sense of that definition. But some sort of something to define what it means. And what I did there is something Well, y'all are perfectly capable of, and it will make a big difference on your way through school if you take time to do that. We see those technical definitions, especially the ones that are kind of vague and not very helpful at all. Make up your own definition. How do you define that word? Like the definition of computer. I want to put in these notes today. I know. So if we look at actually go look up what the definition of computer is. I have a definition I often use in the SF 120 class. Definition of computer. Electronic device for storing and processing data, typically in binary form, according to instructions given to it in a variable program. Yeah, I guess that makes sense, right? But something like that is, you kind of have to know a lot of stuff already. You kind of have to know what processing data is. You have to know what binary form is. You have to know what a variable program is to really make sense of that. So how would you, that definition would be useless to somebody that did not know what a computer was. So think about that on your way through school, as you see the different definitions of things. Make up your own definition. It's easier when you know things, when you already know what the thing is. So like the stuff we're talking about in this class, like a computer. I would describe it as discrete state machine capable of a discrete state machine capable of detecting change and reacting to change. That's my definition of a computer. It's a machine that can detect a change and react to that change. For example, if I open up the chat room here, I'll do it on the TV because people in the classroom are plugged in to Zoom call. It's in a state. There's a particular state happening in this machine, and if the state changes, like I come over here and push the G key, it detects that change of state, and it reacts to that change of state. That's how I define computers. A machine that can tell what's currently happening and can react to changes. And software developers are software, the topic for today. This is the definition I usually give at the beginning of the introductory software development course. I give that definition and sort of this same spiel about make up your own definition. Could you describe, there's a lot of these technical definitions that aren't helpful at all, really. Could you describe it to somebody that does not know the words in that technical definition? Make up your own definition. It helps with understanding all sorts of things. But the physical device, that's the machine. The data is tracking the state. It knows what state it's in. When it detects change, it can compare the state it's in to the given change that happened. So it, like in the chat room, it knows which one of these keys I'm pressing. If I press several keys at once, it knows what to do on that already, right? That's a determined change. So I'll try as carefully as I can to push like G, H, and J at the same time. If I push them all at the same time, it knows what to do. Which for a chat room, it just ignores that. It's like that was an accident. Keys should be pressed one at a time, not simultaneously. So software is following that definition, my personal definition that I just made up there. Software is where we define what that reaction is going to be. The computer, the hardware detects the state, and the hardware will pick up the change. So we just need to tell it how to react to any change in state. Different ways to approach it. So that's another one, is just come back and try different wordings, right? There's different. English is a very complicated language. For those who English is second language, it's an awful language. Whatever your first language is, I can just about guarantee that if English isn't your first language, people that have spoken that language since birth don't still need help with it when they get to the college level. But any college, if you go to any college in America, the writing center is going to be filled with students getting tutoring help with the language they've spoken since birth. But the trade-off for that, the reason and the trade-off for that is there's so many more ways to say things in English. Right? If English is your second language, you could just say, "Oh, back home we used to say this," and write off something in your native language, and now it's English. We just kind of bring things together. People from all over the world ended up in one place and had to figure out how to speak to each other because American English is not the same as British English, and with French English and all the other. There's all the different Englishes around the world because people just ended up in the same place and have to figure out how to communicate with each other. And the result of that is we have lots and lots of ways to say everything. There's so many more synonyms than we had. It's so much bigger than the other languages. And most people's vocabulary and most people in the world vocabulary is somewhere around 80,000 words. Typical American is somewhere around 400,000 words. So there's way more ways to say things, which opens the door for things like that. If it doesn't make sense, try to rephrase it. Look for synonyms. Go check the thesaurus. Check with the other meanings of those words. Like maybe it doesn't make sense because they used it in the dictionary. They used a word that had 5 different definitions, and you're thinking of the wrong one. So take time to pause and look that up while you're in school. It doesn't take long, especially with Google, right? Just put the words definition or thesaurus right in the search, and it'll get right to those lists for you. And phrasing yourself, which usually involves simplifications. I'm a big fan of that quote from Albert Einstein of if you can't explain it to a kid, to a child that's curious, then really what's the point? It's one thing to be able to explain it to another technical person, but if a 3-year-old asks you the question, can you tell them can you give them an answer? Because in a lot of ways, that's a bit more important. That's the one that progresses through history, because then 30 years later, they'll be telling the 30-year-old, answering the 30-year-old's questions. Just about vocabulary, because I'm very focused on not going down here rabbit holes with software development. My 6 o'clock class tonight, I'm already thinking about stuff for that, and there's all people about to graduate with software development degrees. So can get very advanced in software development in a couple hours. So I got to focus on the intro stuff. Talk about physical devices, how they store stuff, those representations. What the machine actually does is very difficult for humans to work with, right? We spent a whole day in class just talking about how the machine shows the numbers. It turns out it's the same way we did what we learned back in elementary school with the columns and spaced off the same thing, but spaced off too, but we spent a whole day talking on it. And all we did was represent numbers. Except for a few special cases, pretty much only electrical engineers do that. And since building devices is one of my favorite hobbies when I have time, it is very, very difficult, even if you're the electrical engineer of the building. Even if it's a small thing, you only got like 5 bits and a bunch of wires, moving through a bunch of wires. And you're sitting there and you just put it together, it's still hard to keep track of. You still have to pull out your voltmeter or some extra LEDs to keep track of which wires are on, which ones are off. Have notes all over the place about what the different combinations mean. It's a very difficult thing for humans to keep track of. We saw when we were talking about the binary representation, we jumped up to hexadecimal. So usually if we're going to work in binary, we do it 4 bits at a time. So if we had, say, 1, 0. Or this. Nope, that one's going for it. That's probably why it's sitting up here. I need to actually throw that in the trash, I suppose. So if we had 1, 0, 0, 1, 0, 1, 1, 1. We saw last week how we can turn that into a number. if we're going to work with that, like maybe that's something we're going to use in the color, we can break it down. Or as humans, the human propensity to make things more difficult than they need to be comes in really handy here. And we do it with 4 bits at a time instead of 1. We make it more complicated, and that works a lot better for us. These 4 bits, 8 plus 0 plus 0 plus 1 would be a 9. 0 plus 8. So no 8s. 4 plus 2 plus 1 gives us a 7. So then we're in the hexadecimal base 16, and we can just translate this into the base 10 numbers we know. So we have 9 in our 16 column plus 7 in our 1s column. 9 and 16 is 16 less than 160. 140. 4. Plus, well, 7 times 1 is easy. So 151 is the number we would represent. So we don't go all the way to the binary. We turn it to something easier for us to work with. It involves a lot less steps, right? To add all those up, we'd have the 128 column, 64, 32, 16. There's a lot of different things to keep track of. So it consolidates it. Same thing with 1101, 1010. I wrote this in the margins probably because I jotted this down on the notes and then realized that I didn't use any of the extra symbols. So for base 16, we need 16 symbols. 0 through 9 are obvious because we're talking about numbers. Then we just start with our letters, so A through F. So this one, 8 plus 4 plus 1 is 13. So A is 10. So A, B, C, D. So that should be a D. Then over here we have 8 plus 0 plus 2 plus 0 is a 10. So it gets us back to that A symbol. So if we're going to work with binary, we do that. Makes the conversions a lot easier. When we're doing things directly for networking people, if you're working with addresses, the computers know about each other based off the binary address. So if you're going to read that, you're probably going to put it in the hexadecimal format and read it off hexadecimal. Usually IP version 4 addresses, which use 4 8-bit numbers. That goes from 0 to 255 to get 256 values. We'll see those in base 10, but depends on where you're looking at it. If we're looking at binary as humans, we usually see this, or colors, where we are directly sending voltages to some pixels and not sending voltages to other pixels. We have a bunch of 1s and 0s to represent those colors. How much red, how much green, how much blue. So we look at it in hexadecimal, or I guess in that case, more often we type it in hexadecimal because we have plenty enough buttons. We don't need only 2 keys on the keyboard. In general, though, humans are not very good at keeping track of that. Like I pointed out, even if you're the one that put the machine together, it's still hard to keep track of binary. I will do one quick note here. When you see it written down, 10101, we'll see it written down like that because of the way we normally write things. If you're actually working in binary, you would probably write it like this. And then view it in what we call a timing diagram. So over time, maybe this is, so at the beginning, everything's all. So we have all 0s. Then maybe these 2 channels come on. Then these 2 go up to 1 for some amount of time. These stay at 0. Somehow my numbers got off. One goes back to 0, and this one goes up to a 1 for the next little amount of time. This one stays up with 1. Yeah, so at the start, all of them are off, and then when we get finished over here, that one's on, that one's off, that one's on, that one's off. So if you're working in binary, you probably work with it that way, not written out as one long string, the way we write out English, because it's definitely not English, right? Very, very different than English. So we need a better way to work with that. And there's different layers of abstraction. It's okay if I erase this. I just wanted to point that out, because this just, it looks extra confusing. It's hard to visualize how people work with it. Take them one at a time, and usually something like this, our time intervals split up that way, so we can tell what it is at any particular time. And the rest of this stuff I wanted to leave on the, try to leave on the board if it fits for a minute. So we're not going to work in a machine language. We can take that a step up to what we call assembly language, where there's still some machine level, but we start using some keywords and symbols that mean something to humans. Assembly language. Did I have a summary written here? Combine keywords, or commands with binary. And I'm going to put binary in quotation marks, because in 2023, if we go type in assembly language, the machine, we can type our base 10 numbers and the machine will automatically turn those to the binary when it runs the assembly. So binary in a relative form, we type base 10 and the machine runs binary, or pulls the binary out when we say to run it. With binary data, to do stuff. Like I explained it to little kids, because we want to make sure we can use small words too. There's a much more technical term. To execute an operation would be a technical thing, but there's different layers, and sometimes getting too many layers away, going to that like highest layer, it's just going to confuse you more than it helps. Gives you some fancy sounding words to memorize, but it doesn't necessarily help with your day-to-day job. So for example, add, here's what we're going to do. 2 plus 3 gives us some number. I'm going to write X. This is what we're trying to do for the examples in these things. 2 plus 3 gives us some number. And then we're going to say, is this bigger than, what did I put in my notes? I didn't have something there, so I'll say 5. Something like that. This is what we're going to try to do. Is this bigger than some number? Then target number, that's a good word for it. We have some value in mind. We want to add a couple numbers together and see if the result is bigger than what we have in mind. And obviously in a real situation, we probably wouldn't have 2 and 3 explicitly. We'd have it open for whatever number we ask about. But for simplification on the board, I'm just going to type the numbers directly. So we want to add 0, 0, 1, 0, 0, 0, 1, 1 result. And the machine I copied this from was a 64-bit machine. So I'm going to write less bits. So this with another 60 zeros in front of it. But I thought I'd leave the 60 zeros off for the notes. Part of the reason I went with 2 and 3 as well. So we recognize that a little bit. We saw how to read binaries. We find those numbers. And we know what add is. So even as humans, that tells us that those have to be numbers. Because numbers are what we add. And rest is the abbreviation for result. On the particular machine I copied this off of. Load 0 0 1 1 0 0 1 1 1 0 1 1 1 0 0 1. This is an address in RAM. So the number that adds up to, I was copying when I put the notes together. What do we got here? 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096. What's so much that? 8,194. Whatever the next number is. So we have one of those. So that was a particular spot in RAM where this data started. So we had to take our result and I'm gonna draw a picture. So in our CPU, we have a couple registers. So there's register A, the full adder, that's the thing that does the math. We plug them in, and then register B. So when we want to do math, we take our first number, put that in register A. I'll write a 2 here. We take our second number, put that in register B, and this is just an open circuit. So as soon as we put that number in register B, electricity flows through, and then those two numbers flow through the full adder together. And the result of that replaces what's in register B. And doing so also includes, there's another bit that we flip on and off so it doesn't feed through again. Right? It's a 0, and then we load in a 3. That loop around bit changes to it loops around, and then that loop around bit changes to a 1, so it doesn't happen again. And the result gets loaded right in there. So at this point, register B has the result. So we're going to store it. We're not going to delete it. That's result just means don't delete that number. We have to be very explicit when we give computer instructions, because it would add them together and be like done, and then delete it. Is if we don't tell it to keep that number. So now there's a 5 in register B, and we're going to go over to RAM and load whatever's stored here into the register. So maybe we have a 7 stored there. Let's just say we have a 7 stored there. It'll load 7 into register A for our next step, which when it loads that in, it kind of again flips that little bit, so those loop together, and now we have 7 and 5 loaded in there. It's 12, positive 12. Remember the other day when we were talking about 2's complement, there was that extra bit at the end that I said would get discarded. Actually, in this case that I'm copying here, that's the only bit we care about. We discard the 12 and only keep that plus or minus sign, because then we do jump carry. Where did I grab? Oh, this is the long one. Actually, it needs 2 things. 1 1 0 0 0 1 1 1 1 1 0 0 1 0 1 0 2 dot dot 001 dot 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 001 with 64 bits, so a whole bunch of zeros before that. Same thing here, a whole bunch of zeros before that 16-bit number. So we load in here, this runs through, we have positive 12, and we say jump carry. So disregard the 12, we only care whether that's positive or negative. And that's for comparison. If we wanted to compare two numbers, so all we can really do, we have the RAM, so we can hold on to things, we can hold values, or we have the ALU, the arithmetic logic unit, and floating point unit, so we can do that two's complement addition. And we can combine that to compare things. So like 7 minus 5 gives us a positive 2. 5 minus 7 gives us a negative 2, or 7 minus 7 would give us a 0. So we can tell if things are equal, if the first number is smaller, or the first number is bigger from that. So that's where we would hold on to this sign, and if it's a positive number, which means if that's the result we got, which we saw was positive 12, the 5 loops back around, and now we have a 12 here. Positive 12, jump carry, we discard the 12, we see it's positive, that means our first number was bigger. The 7 was bigger than the 5. So we're going to go to this bit in memory, and then these two reset the registers. Now we're going to undo that result operation and empty those registers back out because we don't need those numbers anymore. That's still a lot to follow, right? Still not something easy for humans to work with. It's okay if I erase this picture. So to take a moment to visualize what's going on in the hardware with that. And well, we have RAM and we have the arithmetic logic unit. So we can hold things, or we can do two's complement math with them. And we can extend that immediately to looking at the result, and we get comparisons. And everything else is built up from those three. Still kind of hard to work with. So then we get into high level languages. I'm gonna move this down to the next level. Dot dot 001 dot 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 001. Then we get to high level languages. I summarized that in my notes. More layers of abstraction. To make it closer to how humans would do the same thing. Make it closer symbolically, the symbols we use are closer to that original question we asked. 2 plus 3 gives us some number. Is that bigger than this other number we had in mind? Well, there's abstraction to make it closer. I'll put quotes. A very loose term. There's other words we could use there. Some of the complexity in human language. We want it to look the way we normally do things. But it becomes problematic if we go all the way to the way we would exactly do it in English. So it's closer to our own. So this same instruction here in a high level language, in particular Python, the one we're going to look at for our examples, we would say target equals something, not sure what. We can decide the target anywhere. When I was writing numbers down, I just wrote a 7 there, so maybe I could put that. Then we'd say X, I'm gonna say equals 2 plus 3. So we're gonna do some stuff with it later. So we're gonna take the result of 2 plus 3 and store it in this value X. So that's when I took a moment here, you see how the same instructions are there. We have two numbers. But you'll notice one big difference is this is written the way we would write it, but a computer couldn't do it that way. As humans, we know when we see the addition sign, we need the number before it and the number after it. But for the machine, it needs to know which operation it's doing. It needs to know it's adding before it looks at two numbers. So the order has to change. So there's that abstraction we put on there. We use the word assignment for one equal sign. Typically, two equal signs means equality. Equal to, same thing. Or the word is fits there nicely. When we rephrase things to try to put a nice algorithm together, alternate wording helps a lot too. So 2 plus 3 assigned to this variable X. I'm talking about what a variable means after a break when we actually get into an example. But we stored it somewhere. Well, there was all this stuff that was actually based off the machine itself. We're going to jump with that. If the carry bit says we have a positive number, back to the machine level itself, we need some abstraction. So in most languages, we use the keyword if. Really, we're not asking the machine, we're telling it. So we use if, but when we're putting things together, it might be better to think of the word is, like I wrote over here. So is X bigger than the target? And if so, then we'll do something. I'll use some proper terms here. So call some method. And we can store things or run them through the full adder. Here we stored a number. A function or a method is where we store a bunch of instructions. So not a full program, just like 3 or 4 lines that we're going to run over and over and over again in our program. We don't want to type them every time we need them. We want to type them once and then just ask for them over and over again. So sort of the same thing. A small couple steps that we saved to a name, same way we stored this number to a name, so we can get back to it later. Looks a lot better this way, right? That's what your homework assignment is going to be in that language. Well, not that one. I think you checked leap years. I have several there and I swap them out. I have several versions of the assignment. I swap them out. I think I put the leap year one in there this time. And in the software development class, you would probably have to calculate leap year. So it gives you the whole algorithm. It tells you type this, copy this file and do this. But please don't use Control-C and Control-V, like actually retype it. Try to think about what you're doing on each line there. You might not be heading down a software development pathway, but whatever pathway you're on, what software development really is telling the machine how to do something. So whichever IT pathway you're on, you are going to tell the machine how to do something. So instead of just hitting Control-C and Control-V to get the code over there, actually type it in and think about what's going on, see if you can make sense of it. But it has that high level abstraction so that it's closer to the way we would do it. Those two things are in the same instruction. This is for a particular machine. This wouldn't work on just any machine, but yeah. I think when I originally wrote it, I had a Y here instead of target. I said Y equals 7, X equals 2 plus 3, X is assigned 2 plus 3. If X is greater than Y, then go to this other method. And I just spit that out. I just assembled that and spit it out in assembly code. Where I copied and pasted that from. A lot easier to work with it here. And this is what we will mostly do in the thing. And one of the things about machines is they remember what they've already done. Not just what we've already done, the machines remember what other people have already done. So this has been building since the 1950s. Programming languages are huge. They have lots and lots of things in there. There's a couple of keywords, what they're built from. I'll look at this real quick before we break. If I go over to my computer where Python's installed, way down deep in the folders, which I'm not used to this view. It's been years since I had the big one, so where's app data? Oh, did I just move something? I hope not. I think I might have moved something. Okay. Eventually get down to where Python's installed, and in this folder lib, there's a particular file here called, well, you'll notice there's lots and lots of files here. These are all Python scripts, kind of like what you're going to do for your homework. There's a particular one called keyword in alphabetical order, IL, there it is. If I open this in a text editor, so we're just going to look at the ASCII code. There's this short list of words here. There's where it ends. So from line 54 to line 18. So 54 minus 18 is what, 26? 36. Yeah, 36 words that mean something to the Python interpreter. We're going to talk about what an interpreter is after the break. But those 36 words are how we would build up everything. But we don't have to start from scratch. That's what all these other files on here are. Some of these look quite the mess. So calendar's not too bad. Open with, and I'm pretty sure I did the leap year thing this time, so I can. Your version of a leap year will not look like this one. So we can combine those keywords with a couple operations and form an instruction, and then anybody can it's saved to a method, that thing I was talking about here. A small set of instructions saved to that function. Yours won't look like this. It's broken down and it looks a lot simpler. But we use those keywords and a few other things to build up instructions that other people can use. And that's what we think of as a programming language, these many files here that have those pre-built things we can use. So we're not always back to the core level. But we'll talk about that after a break, preparing for the thing. There's one more thing I want to talk about before we start working through an example. And like places to write code and stuff, and that's categories of languages, but it looks like it's probably a good time for a break, right? It's been over an hour. Does 10 minutes sound good to everybody? I see big head nods in the class. So 2:04, so we will get back to this at 2:14. I will see y'all in just a few minutes.